Hey guys, this lesson we're going to talk about the counting principle and using tree diagrams to help figure out the number of outcomes also. That's what both are used for, is figure out how many outcomes are possible in a given situation. So the counting principle is multiplying the number of outcomes for each part. It's basically the idea of that, and that'll tell you how many distinct outcomes you have for the entire experiment or whatever it is that you're looking at. The sample space is all the possible outcomes for the experiment, and the sample point, that's just one of the outcomes in the sample space. And then a tree diagram is just helps show the paths of what could happen through each stage of the experiment or whatever it is that you're looking at. So when you flip a coin and roll a die, so let's go back, we're going to talk about the counting principle. Counting principle tells you to multiply the number of outcomes for each piece. So for flipping a coin, there's 2 possible outcomes. And then for rolling a die, let's assume it's standard 6 sides. So then multiplying it, you get 12 possible outcomes. And then what are they? That's asking a little bit more specific. We can use a tree diagram to help with that. So for our tree diagram, first thing we're looking at is on the coin you can get heads or tails, and then after you get heads, we said there are 6 things that can happen on that die that you rolled. You can get a 1, a 2, a 3, a 4, a 5, or a 6. And that same 1, 2, 3, 4, 5, 6 can happen after you get a tails also. So that could be a 1, a 2, a 3, 4, 5, or 6 there as well. So those are, these are your outcomes. You can see that we've got heads followed by 1, 2, 3, 4, 5, 6. That's 6 outcomes there. And then tails followed by 1, 2, 3, 4, 5, 6. That's another 6 outcomes. 6 and 6 would be 12. So listing them out, the tree diagram helps you understand this concept, I think, really good. But you can get a heads with a 1, heads with a 2, heads with a 3, heads with a 4, heads with 5, heads with 6. And you can also get each of those things with tails. So you can get a tails 1, tails 2, tails 3, tails 4, tails 5, and tails 6. So this is your sample space. And going back here, the sample space is all the possible outcomes. We said what they were, and like I said, I think the tree diagrams really help understand what can happen with those. The counting principle is good also, but that just gives you the number of things, but that can make sure that you counting them out, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, make sure that that's 12. All right, at a restaurant, a lunch special consists of a sandwich, beverage, and a dessert. The sandwich choices are roast beef or ham. Beverage are coffee, tea, and soda. And dessert is ice cream or apple pie. So we're going to use the counting principle. We're going to first talk about the sandwich. And with that sandwich, there are two choices, roast beef or ham. And then we'll look at the drink, the beverage. There are three choices, coffee, tea, and soda. And then for dessert, oops, not dessert, but dessert. We have two choices there. So the counting principle is simply multiply. 2 times 3, 6, times 2 is 12. So we got 12 options again. And that's it. It just said how many possibilities. So we don't need to write them all out. If we did, we would just say it would be helpful to do our tree diagram and all of that stuff, which is what we're going to do right now. So for our tree diagram, we're going to start with our sandwich choices. Sandwich was roast beef or ham. And then for each of those, if you choose roast beef, you then have three choices for drink, beverage, coffee, tea, and soda. And then same three choices here. I should probably make those a little bit bigger so I have space. Just spacing them out a little bit so I can fill everything in. So like we said, coffee, tea, soda, coffee, tea, soda. Now for each of those, you also have those two dessert choices from each one. So we've got two branches from each of those. And those choices were ice cream or pie, apple pie. Ice cream, apple pie, ice cream, apple pie. Really should put those together in my opinion. Little pie a la mode. There we go. Ice cream, apple pie. So now we're going to look at our tree diagram. We can see that we have, look, just counting the final row, 2, 4, 6, 8, 10, 12 things. So those are our 12 options. And then our sample space. I'll use a highlighter to show you here. To figure out your sample space, you just follow each path. So we have RCI is our first one. So that's roast beef, coffee, ice cream. And then we follow that down the other branch, RCP, roast beef, coffee, and pie. And then we do our next branch, which should be roast beef, tea, and ice cream, or roast beef, tea, and pie. I'm just going to follow this. I'm not going to highlight it every time, but I'm trying to give you an idea here. So roast beef, tea, ice cream, roast beef, tea, pie. We also have roast beef, soda, ice cream, and roast beef, soda, pie. So that actually takes care of our entire roast beef side. Now on to the other side, which is going to be ham. And now the only thing that's changing here as you look at these is going to be H. So we just got to change all those R's to H's. But we're looking at each branch. We go HCI, followed by HCP, and HTI, followed by HTP, and then HSI, followed by HSP. Ham, soda, pie. And that's our sample space. And again, we listed out all 12 things. Just making sure, check it back with your counting principle, make sure it works out. Should have the same number. All right, so now we're going to see how this ties into like probabilities and things like that. If a customer randomly selects a lunch special, determine the probability that both a roast beef sandwich and ice cream are selected. So we're looking for the probability of roast beef and ice cream. So it has to have all of those. So we know that there are 12 outcomes because we just listed all 12 of them. And now we're going to look and see how many of them have roast beef and ice cream. So looking back here, we have roast beef, ice cream, this doesn't have it. Roast beef and ice cream. Roast beef pie, roast beef, ice cream. And then none of these have roast beef. So it's, erase that so I don't miscount. We had 1, 2, 3 of them have roast beef and ice cream. 3 of them have roast beef and ice cream. You can reduce that to 1 out of 4, or you can write that as 0.25, 25% chance. At a restaurant, same situation, find the probability that neither tea nor apple pie are selected. So the probability of no tea and no pie. So again, we know there are 12 things. We can look back at our sample space. We have no T and no P. So this first one, we'll highlight them this time. No T, no P. Yes, this has a P. This has a T, has a T and a P. No T, no P. No T, but it does have a P. No T nor P. This has a P, this has a T, has it both. That one, and this has a P. So how many of them did we highlight? 1, 2, 3, 4. So our probability, we have 4 that do not have T, and they also do not have P. That's 4 out of 12, which reduces to 1/3, which is 0.333. All right, another big idea that comes with probability is whether or not you replace. So once you take out an object, once you've selected it, can it be selected again? If you can select it again, then that is with replacement. And if you cannot select it again, that will be without replacement. It's like once you select it, you've removed it from the bag. Think about like if a teacher uses popsicle sticks or name cards or something like that, and then once they've called on you, you set it aside, you cannot be called again. It's been removed. There's less things to choose from there. Or like in the lottery, once the number has been selected, or bingo, something like that. Once the number's been selected, they take it out, they set it on the table, and they cannot choose it again. So that would be an example of without replacement, because you're not putting the ball or the popsicle stick or whatever back into be selected again. Alright, so your TV remote has buttons for digits 0 through 9. If you press 2 buttons, how many numbers are possible? If the same button may be pressed twice. So once you select a number, you can select it again. That's with replacement. So you're looking at that. The first button press is 0 through 9, which is 10 options. And then the second button press with replacement, there's still 10 options because you can push it again. So then you multiply it out. That means there are 100 options. And that's not super complex, because if you think of a 2-digit number, you've got 0 through 99. That's 100 numbers. So that should totally make logical sense there. All right, well, what about if you cannot press the same button twice? So that would eliminate things like 0, 0 and 11, 22, all those things. You can't press the same button twice. So it would eliminate those multiples of 11, I guess it would eliminate. So first time you press the button, you've got 10 options, but now the second time you press it, you can't press the same once. Now there's only 9 options of buttons to press. Multiply that out. There's 90 options. Should make sense. You've eliminated 1 from each each tens, basically. Like we eliminated 11 and 22, 33, 44, 55. We've eliminated all of those, one from each 10. If two dates are selected at random from a year of 365 days, use the counting principle to determine the number of possible outcomes if the dates are selected with replacement. So it can be, so we're picking out two dates, and it can be picked twice. So that means we put it back. So the first time there's 365 options. You put it back, which means there's 365 options again the second time. I need a calculator. 365 times 365. 133. 225. It's a lot of possibilities. Now, without replacement, that means first time you can pick any of them, but the second time you cannot pick the same number again, so it goes down by one number. 365 times 3 times 364. 132, 860. All right, so now we'll look at the probability of an event happening at least once. So at least once is just the opposite of it not happening at all. That's all it is. So if it's the opposite, or complement is another word for that in probability terms, we just do 1 minus the probability that it does not occur. Because that would be the complement, it would be the rest of it. It would be all the times that it didn't occur, mean 1 minus all the times it didn't occur would be all the times that it did occur, at least once. So if the probability of not getting any red flowers from the seeds that are planted is 2/7, what's the probability of getting at least one red flower from the seeds that are planted? So at least one is going to be 1 minus the probability of no red. So the probability of getting no red, it's told right here, probability of not getting any red flowers is 2/7. 1 minus 2/7, or you could say 7/7 minus 2/7. That is 5/7. That's it. Go ahead and find your homework in the Files tab, post your comments and questions, and I'll see you next time. Bye.